All right, good morning. Good morning. Great, so I want to start, when talking about last time, with two corrections. So one thing that I said incorrectly last time was when I said, when I was talking about manifolds not having triangulations. So I looked it up, and I should have been much more precise. So we have cell complexes, which are also called CW complexes. And inside these, we have our delta complexes. And inside those, there's what are called simplicial complexes. Right? So remember, a cell complex is just a space built up from a skeleton inductively, right? So you start out with points, and then you have one cells that you attach to those by their boundaries to those points, and then two cells that you attach to the one skeleton by their boundaries, and so on. That's a cell complex. You impose nothing beyond this inductive construction. Delta complex, we have a bunch of conditions that we impose. A simplicial complex, you additionally impose that every time you're gluing a standard n simplex in, all of the boundary faces are distinct n-1 simplices. Right? So, for example, the circle with 1, 0 cell and 1, 1 cell, it's a perfectly good delta complex, but that doesn't count as a simplicial complex because both ends are being mapped onto the same 0 simplex, whereas if you were to take two vertices, then that would be fine as a simplicial complex. Okay, so a triangulation can mean having this structure, or having this structure. So last time I said that it was having a cell complex structure and that there are counterexamples. Right? So that's not correct. There are counterexamples to having a simplicial complex structure. So here's what happens. Every manifold is homeomorphic. No, that's not true. Every manifold is homotopy equivalent over here to a hold on, I'm saying it backwards again. I'm going to look at my notes. Okay, every manifold is homotopy equivalent to a set with a simplicial complex structure, and it is homeomorphic as long as its dimension is not 4. It is homeomorphic to a cell complex. So dimension 4 is strange. So, I'm sorry?
It's the exotic smooth topology?
Well, it's the exotic not smooth. So yeah, so you can divide structures on manifolds into, well, you can look at algebraic or analytic, but generally you talk about smooth, piecewise linear, and topological. And in dimensions up to 3, if you have any manifold, it admits a smooth structure. So there's no loss of generality assuming things are smooth. In dimension greater than 5, you just have this division, all 3 are different. And in dimension 4, things are just crazy. So you have, for example, any space, any manifold, homeomorphic to Rn is diffeomorphic to Rn unless n is equal to 4. If n is equal to 4, then there are spaces, there are uncountably many spaces that are homeomorphic to R4, but not diffeomorphic to R4. So exotic smooth structures on R4. And it's the only dimension where that happens. Okay, so if the manifold is smooth, If the manifold is smooth, then not only is it homotopy equivalent, but it's actually homeomorphic to a simplicial complex. And that's what's known as a triangulation. So triangulation of M is a homeomorphism to a simplicial complex. Okay, so then the fact that I was misstating last time is the following: if the dimension is equal to 4, then there are non-triangulable manifolds. That's due to Casson, and there's an explicit example called the E8 manifold, and well, somewhat explicit. There's an example, we have a name for it. So in 4 dimensions, it turns out Friedman proved and got the Fields Medal for showing that the manifold is determined by its intersection form. Anyway, next semester I could tell you what the intersection form is. But so this is explicit in that we know which intersection form corresponds to this manifold. Okay, if the dimensions, and this one was the example that Friedman gave of a topological manifold that admits no smooth structure. Okay, and then the recent thing. So this was done in 1990. So what's recent is that for this is also true for all n greater than or equal to 5, and that was proven by Manolescu in 2013. Okay, so, but what I was saying yesterday about using cellular homology to compute the homology of manifold, that actually is fine, because unless you're in dimension 4, you're always homeomorphic to a cell complex structure. And even in dimension 4, it is homotopy equivalent to a simplicial complex. And homology doesn't notice homotopy equivalences. So, okay, so that's the first correction.
Wait, sorry.
Yes.
So is this not true if the dimension is less than 4?
Oh, sorry. If the dimension is less than 4, then all manifolds have a smooth structure.
Okay.
And so it doesn't. It's all easy. Everything is nice. Okay. So, okay, that's the first correction. So the second correction was a question that Christian asked me when I was giving the proof of the theorem from the lemma. So let me remind you what we were doing last time, and then I'll get to the correction. Okay, so we are studying orientability with coefficients. So we're using the concept of the section of a covering. So if this is a cover, a section of pi means a map say S for section that goes the other way, such that if you start at M, you go up to X by this section, then you go down back to M. This is the identity. Right? So it's a one-sided inverse of the projection map. Right? So a better way to draw that is that you have your projection map, you have the identity map, and a section is any lift of the identity. Right, so anything that makes this diagram commute. Okay. So if R is a commutative ring with identity, then an R orientation is a compatible choice of generator of the local homology with coefficients in R, which we know is always isomorphic to R for all x in the manifold. All right. So equivalently, an R orientation is a section of the covering space you get from the local homology groups with coefficients in R, valued in the units. Because remember, for a generator, when you're working with a ring, what you want is just a unit. So just an element U, such that R of U is equal to R, which is the same as saying that U is a unit. OK. So it's equivalent because the compatibility is exactly what we used to put a topology on the covering space. So continuity of the map going up to the covering space is the same as compatibility of the choice of elements. OK? OK. So in particular, well, let's say a source of sections well, let me say that. OK, so here's the lemma. So M is a manifold, not necessarily compact. A and M is a compact subset. And these got numbers or letters. Numbers. So if we have a section then there exists a unique alpha sub A in the homology relative to A that induces the section. So this is what I was about to put as a way of obtaining a section. Well, if you have an element in here, then every point x, every point x inside A, I can look at the local homology at that point x, and it receives a map from this group, from this ring. Well, actually, I don't. Depends on what A is, whether that's R. But it receives a map from this ring, just by the inclusion map. And so that gives us an alpha x. So the claim is that all of these individual elements of the local homology groups can be amalgamated together into a single element for any compact set. So that's part one. Part two of the lemma says that hi of m minus a, coefficients in R, is equal to 0 if I is greater than n. Okay, so that's the lemma. And with that lemma, we're proving the following theorem for M compact and connected. So it says that the if M is orientable directly, yeah, if M is orientable, then for all x in M, the map into the local homology is an isomorphism. Here I should say if M is R orientable. Then this map is an isomorphism. In particular, since this is R, the topology group is R. B, if M is not R orientable, then this map is always injective with image so the image is a subset of the ring R, and it's all of those elements in R such that 2R is equal to 0. And then the last part says that in any case, HI of M is coefficient in R is equal to 0 for all I greater than n. Here, n is the dimension of the manifold. Okay. So last time when I was doing the proof of the theorem from the lemma, I said that, I stated things for an arbitrary ring R, but then when I was doing the proof, I was assuming that R was the integers, just out of habit. So I said that, okay, well, since this is connected, the values of a section are going to be determined by what they do at a point. And so then you look at what are the possible sections when you're not R orientable, and the only thing you have is 0. The only possibility is 0, right? And so I concluded that the topology group was 0, right? Which is great for the integers, all right? But Christian asked, okay, well, what happens if you have C mod 4? And well, of course, the theorem doesn't say that the topology group is 0. It says that it is all of the elements in R such that 2R is equal to 0. So what happens when you have C mod 4 is indeed the element 2 gets multiplied by 2 and you get 0, which means that that part of the covering space is just a copy of M. So you do have a section that lands in there. And so, in fact, the correct statement for C mod 4 is if M is, let's write the top homology with coefficient C mod 4, assuming that M is compact and connected, is either C mod 4 if M is orientable in the usual sense over Z, and if not, it's C mod 2Z. Right? Which is indeed what the theorem says, and what the proof gave us, because a section can only be valued in the 0 subcover or the 2 subcover. Okay, so that's the second correction. And that's what we were doing last time. Questions on last time? Yes?
Do we find this material in some textbooks?
Yeah, it's in Hatcher in section 3.3.
Oh, in 3.3.
Yeah. Yes, so I've posted the final homework. And so there are 3 problems on orientations from section 3.3. So.
The final number?
Yeah, because then we're out of semester.
Next week is the final week?
It's the last Thursday.
Yeah, the next
Seriously?
Mhm.
Wednesday is the last
Okay.
like the end of April. Wow.
Yeah, the end of April basically is it's still ends early. That means there's finals before that. It's still ends. Yeah.
Okay, so we left off proving these lemma. Right, so let me remind you where we were proving the lemma. So the first thing we did was to note that if the lemma holds for A, B, and A intersect B, then it holds for A union B. Right, so the lemma talks about some compact set. So, well, if you have two compact sets and you know it for those and their intersection, then using Major-Vietoris, you know it for the union. Right? So that let us restrict to a compact set included in a coordinate chart. Right? So using that, we were able to replace M with Rn, because you could just be working entirely in the coordinate chart. And that's where we stopped last time. OK, so now let's assume that we are working on Rn, and we want to prove the lemma. So another case is if A is a finite union of convex compact sets. Okay, so if it's a finite union of convex compact sets, and since the intersection of compact convex sets is a compact convex set, it's enough by this to prove it for a single one. Right? It suffices to prove lemma for a single compact convex set. Okay, but in that case, if you have a single compact convex set, then you can pick a ball containing A, and you can deformation retract both Rn minus A and Rn minus a point, any point in A, to Sn minus 1. And so then the map from Rn minus A to Rn minus X. It's an isomorphism because both of these are compatibly isomorphic to Hn minus 1, Sn minus 1 coefficients in R. Yes?
For this to work, do we need X to be in the interior of A?
No? Where do you want to use? I'm not using excision here. I'm using an explicit deformation retract.
Yes, but if A, one moment, if X isn't in the, oh, Rn minus A.
Yes.
Okay, I was picturing A minus X for some reason.
Right, no, Rn minus A. Okay, so that takes care of that. So we're fine if our compact set is a finite union of convex compact sets. So now for an arbitrary, so finally, for an arbitrary A in R and compact, so consider a class inside the homology of Rn. Sorry, this is actually true for all I. I need it true for all I because the lemma is not just about the top group, it's also about all of the ones above. So given a class, and here we can represent it with a relative cycle. Remember that means that Z is a cycle with the property that its boundary is a cycle in Rn minus A. Right? So when you're doing homology without it being relative, then you would have a cycle meaning that its boundary would be 0, a chain whose boundary is 0. Right? But when you're doing homology relative to some set, then you always have representatives where you have a chain whose boundary is just a chain in that other set. Right? Okay, so by compactness, there's actually some distance. There is a positive distance between the image of boundary C and A. Right, so we're in Rn, we have our subset A, we have a chain Z, and we know that its boundary lands in Rn minus A. Right? So because A and the boundary are both compact, then that means that this boundary sitting out here somewhere, there's some positive distance between it and the compact set. Okay? So cover your compact set with balls, so convex open sets, all of which have a closure that stays within delta over 2 of A. So cover A with finitely many compact convex sets that stay within, say, delta over 2 of A, and let's give that a name. L. Let L be the union of these compact convex sets. Okay, and let K be the image of the singular simplices in boundary Z. Okay, so L and K do not intersect. So K is inside Rn minus L. So Z defines an element of hi r and Rn minus L, call it alpha L, which maps to alpha. Alpha is the class represented by Z. Okay. So, since A is inside L, Rn minus L is inside Rn minus A. So, if this alpha L is equal to 0, right, then by the same relative description, this tells us that Z is actually equal to boundary beta plus gamma, where beta is a Ci plus 1, is a chain in Rn, and gamma is a chain in Rn minus L, which is contained in the chains in Rn minus A, which would imply alpha equal to 0. Right, so we've represented our class. Well, we've taken a representative of our class and seen that it represents an element here. And if that element vanishes, then the one we started with vanishes. Right? So now if, I shouldn't erase this. Okay, so we're done with C then, because if I is greater than n, then by the previous step, alpha L vanishes. So alpha vanishes, and hence hi of Rn minus A vanishes. Yeah. Right, this is the theorem that I'm not erasing. Yeah, I erased the lemma. Oh well. Okay, so if I is greater than n, then alpha L is equal to 0 by the previous step. So alpha is equal to 0. And since alpha was arbitrary, we get that hi of Rn minus A, our coefficients is 0. So that's the last part of the lemma. And so for the first part of the lemma, we have to consider the case I equals n. So if I is equal to n and you have a section so then there exists a class in Hn of m minus b bar, representing, so call this alpha b. Representing alpha x, this is for any B a ball containing A. So we can take alpha of A to be the image of alpha B in Hn m minus A R. So this will represent this section just by commutativity of the inclusion diagram. So we just need to prove that it's unique. So if alpha A prime is any other, let beta be the difference, okay, so then beta maps to 0 in the local homology of every point in A. Hence, it maps to 0 in local homology of every point in L. So L, yes, L is the union of the convex balls, compact convex balls covering A. And the point is that every one of those intersects A and contracts down. So by the previous step, this beta would map to 0 for every x in there. And so by the previous step, beta is equal to 0, which gives us uniqueness. Okay, so that proves the lemma. And the lemma tells us that orientability, if you are orientable, then the top homology group is isomorphic to the local homology group at any point for compact connected. Right? So that means if we pick a generator of the top homology group, we get a generator of all the local homology groups. So if M is R orientable, so we give such a thing a name. We call it a fundamental class. So it's an element, usually denoted square brackets around M, sitting in the top homology that maps to a generator for every x. So this is often used as a definition of orientability. Orientability means that you can pick a fundamental class which generates all the local homology. Right? So consistency is automatic. You could ask for a representative when M is nice. So for example, if M is a delta complex or has a delta complex structure. Okay, so in this case, it would be exactly what you would expect from the picture, right? So if we draw a picture and then we represent an orientation by a bunch of arrows, right? Then what a fundamental class is a choice of all of those arrows that are consistent. So that means that, well, here's what it means. If M has a delta complex structure with finitely many simplices, which is automatic if M is compact, then an N chain is represented by a sum of AI sigma I. Well, let's write it like this, sigma I n. So sigma I n is an n simplex from the delta complex structure. So on the one hand, we can see that each AI is either going to be plus or minus 1, since this must map to a generator of Hn m minus x. R, just pick, let's go with integer coefficients so I don't get confused. And just pick an x in the image of the interior of this. So then the only one that will matter is its coefficient. So it has to map to plus or minus 1, so that coefficient must be plus or minus 1. So that means a fundamental class must be of the form sum plus minus 1 sigma n I. And it must be a cycle. So we need to be able to choose the signs so that the boundaries cancel. Right? So if you think of a surface with made up of a bunch of triangles, then you're picking the orientations of the triangles so that neighboring triangles cancel out the edge in between them. Right? So if it's going one way for one circle, then it's going the other way for the next circle.
What if you can't do that using plus minus 1 code?
Then it's not orientable. So this is possible if and only if n is orientable. Right. Which brings us back to like the intuitive notion of what it means to be orientable, right? Is to be able to pick orientations on all of the little circles in a compatible way, right? So that's exactly the same as this notion of orientable, right? Of course, if you choose C mod 2 coefficients, then you don't have to worry about the signs, right? So for C mod 2 coefficients, a fundamental class is just a sum of all of the n cycles, all of the n simplices in the delta complex structure.
That always be in kernel of the boundary?
Yes. Okay. Okay, so great. So the theorem was for compact manifolds, but the lemma was for non-compact manifolds. So let me point out that if M is a connected non-compact manifold of dimension M, then it's still true that the homology vanishes above the degree of the dimension. Okay, but maybe I won't do the proof. So you can look it up in Hatcher. It basically uses excision. It's the same strategy as for this case. You do it one cycle at a time. So you pick a representative cycle, and then for that cycle, you use excision to reduce down to a compact set. And then you just deduce it from the compact case. Right, which is why we can get the the vanishing part, just like over here, the vanishing part was easy to reduce to a single cycle, just to see that that cycle was 0. Whereas to prove existence, we needed to use this compact set larger. Okay, but that is true and good to know. Okay, so that's all we want to say about orientability for the moment. So next, here's the formal viewpoint, it's called. So in 1945, Eilenberg and MacLean invented category theory. To do algebraic topology. So category theory comes from algebraic topology. They in particular wanted to make sense of what it meant for maps to be natural. And that's where category theory comes from. Saunders, MacLean, and Samuel Eilenberg. Samuel Eilenberg was a member of Bourbaki. So just on the off chance that you haven't heard of Bourbaki, I thought I'd tell you who he was. So Bourbaki is a member of the French Mathematical Society. He was refused, apparently applied for admission into the American Mathematical Society, but he was refused on the grounds of not existing. So back in the 20s at École Normale Supérieure, there was Cartan and Vey and a bunch of people in a first-year graduate class. A person walked in looking rather disheveled with a big beard and started giving a lecture with a very thick accent meant to prove a theorem of Bourbaki. Bourbaki referring to the general in the French army during the Second Empire. It turned out that this person was not a professor. It was just an older student who was playing a prank on them. But they apparently enjoyed it a lot, or remembered it very well, because a little bit later, when they were professors, so the story is that they were at a conference, and Cartan and Vey were commiserating about how hard it was to teach analysis, because the only textbook had been written like before World War I, and so it was just doing everything wrong. And so they decided, what we should do is just write a textbook ourselves. So they got together with some friends, a lot of beer was had, and they got carried away. So they decided, okay, well, really, if you're going to teach analysis correctly, you really should set up a lot of background knowledge that people should have. So they started writing a book on set theory, and then on logic, and then all sorts of things. They never got around to writing a textbook on analysis. But so they decided that they would write these books together. So they invented Bourbaki, named after the French general. André Vey's wife came up with a first name, Nicolas, and so they started publishing these textbooks in this guy's name. Apparently, sometime later, there was a journalist was going to publish a story outing them, and they decided to strike first. So what they did was they hired an actor, and they had this actor come to ENS and give a seminar under the name Nicolas Bourbaki. And so he gave a seminar on Bourbaki work and then denounced the journalist as a fraud, that it was really a collective of journalists writing under an assumed name. So, yeah. Bourbaki does have an office at ENS, and there is a seminar, the seminar Bourbaki, which does an excellent job. They get people who've done very important work, and then they have somebody else come and lecture on that person's work. And so it's really, they pick a good expositor to talk about this. So you can find online, sometimes papers are posted to the archive and it says for the seminar Bourbaki. And so those are really well worth reading. Okay, so anyway, so Eilenberg was one of these Bourbakis. He actually was from the second class of Bourbaki. He was brought in to do algebraic topology, because naturally if you're going to teach analysis, people should really understand algebraic topology. Okay, but they invented category theory precisely to make sense, for a framework for algebraic topology. So here is definition. Category consists of some objects, like this. And for every x and y objects of C, a collection of morphisms. Morphisms, of course, is just a name. It's just a collection. This has the property that for every object x, there is a distinguished morphism in morphisms XX, which we call the identity, right? But of course, it doesn't have to be the identity. It's just some distinguished element. And we have an operation of composition. Well, an operation that we call composition. It says that for every x, y, z, we have a map.
Wait, sorry, does it say 3?
It does say 3 because this is 1 and this is 2. Thank you. Yes. Okay, so there's objects, there's morphisms, and there's composition. Thank you. There is an operation. That goes from the morphisms of xy times the morphisms of yc to the morphisms xz. So it's like a composition. Such that, well, it's associative. And it commutes with identities. Well, and the identities act like identities. Okay, so that's it. That's what a category is. So, of course, the category of abelian groups is just objects are abelian groups, and morphisms are group homomorphisms. Right? Or the category of topological spaces, where your objects are topological spaces and your morphisms are continuous maps. Right? So in both of those cases, the morphisms are morphisms, so not surprising. Of course, that doesn't have to be the case. You can have, for example, if G is a group, then we can define a category with a single object, I don't know, call it X, and a morphism for each element of the group with composition being just the group operation. Right? So I don't really have morphisms from the point to the point. I just have arrows, right? I just have points and arrows, and I have an identity, and I have a composition that's associative. So I satisfy the definition. Right? So we call things objects and morphisms, but it's just a gadget that satisfies those properties. All right, so across the picture. Picture is that you have a single point and one arrow from that point to itself for every element of the group. So we generalize this in a couple ways. So if a category has only one object, so you could think of this as a group without inverses. Right? Because the definition of category tells us that multiplication, which think of the composition as being a multiplication of the arrows, it's associative, but there's no axiom giving us inverses. Okay? So think about this as a group without inverses. This is called a monoid. You could generalize this the other way, because here we have one object and every arrow has an inverse. So, okay, let's say that you relax the fact that there's one object.
Wait, I thought you said there's no inverses.
So that's in this case. So here's another case. So for a group, you have inverses,
Yeah.
right? So, okay, we're going to generalize a group in two directions. We're going to pick one aspect we like, and we're going to ignore everything else. If we keep the fact that it has one object, then there's no reason for things to have inverses. We call that a monoid.
Okay.
A different generalization, let's relax the fact that it has a single object, but let's keep the fact that it has inverses.
Okay.
So a category where every arrow has an inverse, well, morphism. The morphisms are called arrows. As an inverse is a groupoid. So we've seen an example of a groupoid. The motivating example of groupoid which is the path groupoid. Right? So if you think way back when we did the fundamental group, we had the fundamental groupoid. Yes?
Didn't you also say that was the only example? Every
Well, I might have.
Wait, sorry, I still don't understand what it means for the morphism to have an inverse.
Yeah, so in an arbitrary category, you have identities.
Yeah.
Right? Every point has an identity. And you have a composition, right? So I can multiply arrows, and there's this particular arrow, which is the identity. So one arrow is the inverse of another if their multiplication gives you the identity.
Okay.
Right? Yeah, so in a category, it makes sense to ask if there's an inverse, but it's not automatic, it's not imposed. Right? Okay. Okay, functor. Between two categories. C and D is, well, okay, a category has two collections, objects and morphisms. So this is going to be a map on objects and a map on morphisms. All right, so given given I don't know, A in C, we get f of A in D, and given f in the morphisms between A and B, we get f of f in the morphisms between f of A and f of B.
Should A be in an object system?
It should, thank you. Yes, thanks. Where, of course, f of the identity at an object should be the identity at the corresponding object, and f of a composition should be the composition of the f's. Right? Yes?
Do you have arrows or tildes or?
Oh, that's just an arrow. So it's I'm doing a curly arrow for no good reason. It's just from here you go to there. Yeah.
Is that the standard?
No, it's, yeah, I mean, we could have written this. Well, let's leave that. So a better thing to do would have been to write like this. Objects C, objects D, and A maps to f of A. So this diagram is what I'm abbreviating by putting that arrow. And similarly for the morphisms. Okay, so it's what you would expect. It's a map that preserves all of the structure. The structure is that we have identities and we have composition.
So in essence, it's a category homomorphism.
It is. So yes. So soon after categories were invented. So this was 45. In the 60s, somebody came up with the idea, well, categories form a category. And then you could use that to like put foundations for all of math. So there was a lot of work on that in the 60s and 70s. Yes. But in any case, I should mention this is covariant. This describes a covariant. Functor. A contravariant functor reverses arrows.
Wait, what's this?
This definition,
Oh.
yeah. A contravariant functor is something that preserves the structure of categories, but it reverses the direction of arrows. So, i.e., it's a map from C to D, meaning that I have a map between objects of C to objects of D. And what's different is that the morphisms between two objects get mapped by f to morphisms between f of B and f of A. So contravariant, you should think dual.
So a contravariant functor is not a functor?
It is a functor. It's just a functor that reverses arrows. There are two types of functors. There are covariant functors and contravariant functors.
This definition
And
is
of a
not,
covariant functor.
okay, so really the definition of a functor stops before the morphism thing?
So I should have done something like a covariant
Okay.
in parentheses. So if you just talk about functors, you usually just write covariant. And of course, you can write, so there's an operation on categories where you take the opposite category, and then a contravariant functor is a covariant functor. You just have to take the opposite category. Okay, no, so it's very simple. Okay. It is, so, a covariant functor is a functor where you have, like homology, where you have induced maps that go in the same direction. A contravariant functor is like taking the dual of a vector space, or where you take matrices go to their transposes. So,
So did you say if someone says, oh, this is a functor, generally they're referring to covariant?
that's right.
Okay.
Yeah, if you don't put any adjective, then you think covariant. Yeah.
Then the map between, for Galois theory, the map between fields and groups is a contravariant?
Contravariant. That's right. Yes.
Wait, what was that?
So Galois theory, or covering spaces and subgroups, those are order reversing, and so they're contravariant.
If you have subspaces of a vector space, and then you take the annihilator of those vector spaces, that's contravariant.
That's right. Very good. So, but we're doing so homology is covariant, and cohomology is contravariant. Okay. Da-da-da-da-dum. Okay, so indeed, examples of functors. We have singular homology groups. So let's write it like this: Hn from the category of topological spaces to the category of abelian groups. Okay, so what we're going to do is we're going to consider the individual homology groups as functors. You can consider the whole sequence of homology groups as a single functor if you wanted to. Right, so saying that this is a functor, and so again, we're just going to talk about covariant functors right now. So the usual ones, right? So it's covariant. So if you have topological spaces, you get abelian groups. If you have a map between topological spaces, you get a map between the homology groups, right? And those maps preserve the identity and composition. Another example is abelianization from groups to abelian groups. Right? So to every group you assign the abelianization, you mod out by the commutator subgroup. And again, maps between groups induce maps between their abelianizations because a homomorphism between groups sends commutators to commutators. Right, in the fundamental group. Goes from, again, category of topological spaces to the category of groups, not necessarily abelian. Right? And same story. We've seen that if you have a map, continuous map between topological spaces, you get an induced map between the fundamental groups. And the identity goes to the identity, and composition goes to composition. Right? So you have a function. Okay. So the whole point of category theory was, at first, was that you want to make sense of statement like the family of morphisms Okay. Let me preface that with, we want to make sense of. So say t of x, yeah, between f of x and g of x is natural. Right. So you have some functor, some other functor, and an object. And so you can think, for example, of the connecting homomorphism in the long exact sequence in homology. Right? So we've used many times that that is natural, meaning that if you have a map between spaces, between pairs of spaces, say, you'll get a map between long exact sequences, and it'll commute. Right? So we've used that over and over and over. Right? And we just say it's natural. Right? So that's what Eilenberg and MacLean wanted to make sense of, or wanted to define. What does it mean to say that you have a natural construction? Or so they define natural transformations between functors. Okay, so here the setup is you have two categories. Okay, maybe I should start with an example. E.g., the boundary map. So we have pairs of topological spaces and abelian groups. Right, so XA, so this is going to be the relative homology group. HN is going to go to HN of XA. Let's denote that HN rel or something. Let's denote the functor HN rel takes a pair and gives you HN of XA. Right? And then you also have HN minus 1, and I don't know, let's put a 2 on top or something. It's going to take a pair. Pairs of topological spaces, X and A, and it's going to map into abelian groups again. And what it's going to do is it's going to take HN minus 1 of A. Right? Hence the 2. It's just taking the second entry. Okay, so those are functors. And the boundary map construction, the boundary map construction in the long exact sequence of a pair, right? So HN XN boundary to HN minus 1A, right? This is a map between these two functors. Right? So, of course, a map between functors, I really mean a collection of maps, so that you give me whatever pair you want, and then I get a map between the values of the functors on those pairs, right? Between these two functors, meaning HN rel and HN minus 1, 2. Right? So the way this is denoted sometimes is you have, so we have pairs, and then we have abelian groups, And so we have this functor hn rel, and then we have this functor hn minus 1, so 2, and we write like this, a map between those arrows is a bigger arrow. And this would be the boundary map. Okay. Okay, so let's write this as a definition. So given categories and functors, so again, no adjective, so I mean covariant functors. A natural transformation between them is a collection of morphisms, T x f of x to g of x. So for every object in our first category, right, so i.e. really what we have is a map from objects in C to morphisms in D. Such that for every x and y in objects in C, f of x, that's right, like this, g of x, and f in morphisms xy, little f of y, t of, no, what? G of f, g of y, t of x, t of y commutes. It's also with Eilenberg-MacLane that we start using diagrams and proofs and just saying this diagram commutes as a technique. That was MacLane who popularized it. So what you have for a natural transformation is just like over here. We have this map. For any choice of pair, you have a map. And if you have maps between pairs, then the corresponding long exact sequences, but in particular the corresponding square, commutes. Right? So that's what we mean by a natural transformation, is you have two functors, and then for every choice of object in X, you get a map between the corresponding objects in D, such that these diagrams all commute. Right? So that's what we mean by a natural transformation.